all to this quick seminar on COVID-19 dynamics. And today is a pleasure to have the talk given by Dr. Alexei Tkachenko. He's from the Brookhaven National Laboratory, specifically from the Center for Functional Nanomaterials. He works essentially in problems of theoretical soft condensed matter with a special focus on programmable self-assembly and biological inspired nanotechnology. He was postdoctoral research at University of Chicago, also at Lucent Technologies. He has ample experience in these areas. And now with the problem of COVID-19, he's dedicating, as we will learn from his talk, to the solution or to contribution to the solution of this problem from the population dynamics of the infectious disease point of view. So welcome very much. And one thing is this as a talk, obviously the opinions of our speaker are his own and do not necessarily represent the point of view of the project of COVID-19 of National University of Mexico nor the National University of Mexico. This is an academic meeting, so the interventions at the end of the talk will be academic in nature, and of course respect and all the policies of sound academic interactions are here respected. So with no more to say, Alexei, please, the screen is yours.
Okay. So first of all, thank you for inviting me to Mexico City. I always wanted to visit, you know, never had a chance. Well, I hope I will still at some point. As most of you, I guess, I'm a physicist, and most of you, I wouldn't ever believe like half a year ago what I would be telling you about today. So for me, the story started almost exactly half a year ago. So it's middle March. I mean, I'm close to New York City, and of course we are in the midst of, or in the beginning of this epidemics here. And as many physicists, especially statistical physicists, of course, we're trying to make sense of what's happening around. Then the way I switched from amateur to pseudo-professional is thanks to my friend Sergei Maslov, who is in University of Illinois and who is well a good friend of me, and also my collaborator on many projects, including such exotic things as origin of life. So in the beginning of March, or in the middle of March, as I'm looking at this as mostly academic problem, and honestly, I mean, back then my major motivation of understanding the COVID-19 epidemic was not so much the epidemic itself, but to understand what can be done in future epidemics. Because I mean, it was clear from very beginning it will not be the end of the world, but it was very frightening in the sense that if this occurs with much deadlier virus, we found ourselves absolutely incapable of dealing with this. So I was curious from learning something from this epidemics for the future primarily. So again, so I looked at this for I guess a week or two as purely academic exercise until it became very real. So this is the team of 7 physicists with whom we talk every day for the past half a year. 2 of them are Sergei Maslov and Nigel Goldenfeld, made this thing real by basically getting very scared. So they get scared early because by some reason people are not very impressed, but were not very impressed by exponential growth, and of course physicists are. So they applied a lot of pressure on the a management in the university to shut down university as fast as possible. And then the same pressure was applied by them to the governor of Illinois. As a result, the Illinois closed on March 20th, which incidentally was pretty much the same day as New York closed. But what happened is epidemic came to New York much earlier. So what was very late action in New York was actually fairly timely action in Illinois. So what you can see here is Nigel on the press conference of governor, but this press conference is not in March. It's already 1 month after that. So the topic of this press conference was why we should keep, why Illinois should stay closed, right? So it was already back then, after 1 month of strict quarantine and stay in place order, of course, people were eager to get out. And between the 2 points, when they managed to close the state and between this press conference, which occurred on April 20th, we basically developed the model of epidemics in Illinois. Developed essentially from scratch because honestly, I mean, yes, we are all physicists. In fact, 2 of us, Sergey and Nigel, they work a lot on biology. They worked a lot on bacterial communities, for instance, etc. 2 of us are soft matter physicists or soft matter scientists of sort of broader, somewhat from somewhat different subfields. And another 2 of us, well, graduate students, are actually they have completely different background. They are astrophysicists, and then 1 more graduate student is actually Sergey's graduate student who joined us somewhat later. So anyway, given this background, of course, we knew something about epidemiology, but definitely we are not experts in the field. So within that month, and we had to not only grasp the essential concept of things that were developed, but trying to, well, to advance it a little bit further. As you can guess, it's non-trivial because the field itself is essentially 100 years old. So here is the outline of the model that we used back then, we constructed back then. Of course, by now, almost anyone have heard of this standard or basic compartmentalized models in epidemiology. This is somewhat different. So this is actually, this model is just, in its basics, is just as old as the well-known SIR model. It originates from the same paper, in fact. This is so-called age of infection model. I know that many of you probably have heard of it, but I will review. So their idea is the following. So the engine of the epidemic is this renewal equation. In other words, the new infections today will determine infections sometime afterwards. This J of T here is called daily incidence, so number of daily incidents, so number of new infections per day. Depending on how many daily incidents there were 5 days ago, let's say, I can tell you how likely that to have new incidents today. So this equation, of course, is just integral equation. It's almost linear. In what sense? It is linear, so new incidents are just linear in previous incidents. What you don't know here is first this kernel K, which is a distribution function for what is known as generation interval. So essentially, what is the probability that after, let's say, 3 days of getting infected, you will infect someone else? Then another parameter here is RT, which is a basic reproduction number, which depends on time. Now, and then another parameter is number of susceptible in the population. Honestly, this is not exactly, this is not conventional way of writing this. More conventional is to combine RT and S into a single parameter, which is called RT. So yeah. Now, of course, due to the change in susceptible population, these equations are no longer linear, right? The number of susceptibles actually depends on how much incidents have been before that. But at least early in the epidemics, you assume that almost anyone is susceptible. So again, this simplifies life. So simplifies life for modeling. You essentially, you disregard this dependence on susceptible. You just say, okay, you have linear integral equation. It is a very simple mathematical problem, right? The complications come from the following. You don't really have anything measurable in this equation. So this parameter J is hardly known to you. You remember these early days of epidemics when every day a case count would come in. But then you would, of course, realize that that case count depends on how well you test your population. So there is no way of extracting it directly, this daily incident or daily infection from that data. So then the harder, the more reliable data is how many people actually get hospitalized, how many people have died. Of course, all those parameters are coming much later. So a lot of challenge for us was not so much writing the model, right? As I told you, it's in its core, it's linear integral equation, but calibrating it properly and getting the access to proper data. So that was the essential challenge, especially in early days. Now, as I already told you, the equation itself is not new. It's almost 100 years old. I mean, in application to epidemiology, and even older if you ask when it appeared in mathematics. What we also did, which was not entirely conventional at that time, is we used this integral equation presentation not only in order to describe this feedback loop, right, when old infections generate new infections, but also to describe all the responses downstream, right? So for example, what's happening here? Let's understand. So this triangle here is representing the rate with which new infections appear. This triangle here represents the rate with which new people with symptoms appear. Now, of course, we now know, and we knew back then, that some people will not exhibit symptoms. So that's why there is this coefficient here, P sigma, that tells you what is the probability of being symptomatic, right? Then, with certain probability, a person will go to a hospital. When you see this dashed line, you again have to use this integral equation that tells you what is the probability if you develop symptom today, what is the probability of you getting to hospital 3 or 5 days afterwards. So the more conventional way of describing what you hear, what you see here is by drawing all kind of very similar diagram but different by describing the number of people, let's say, who are in hospital, the number of people who are symptomatic, and then assigning just some rates of going from one compartment to another. That turned out to be a limiting, not particularly good approach for modeling. Why? Because it implicitly assumes that all transitions between two compartments is described by simple exponential decay. That is not really the case. So you can, in principle, model a more complicated kernels by having several compartments connected together. But then it means that in order to vary, in order to fit your data, you will need to change the topology of the network. That is also not particularly attractive possibility. So we have this fixed topology, which is very, very simple, and that's almost conventional. So we have people who go to hospital, then some of them will get recovered, some of them will go to intensive care unit, will die, and go back to hospital. Each flux here is our variable, so it's time-dependent variable. That this number of people, H of t, is the number of newly admitted people to hospital. The C of t is number of newly critical people. And then D of t is number of daily deaths. Of course, we quickly figured out that almost everything that is reported with strong delays. And that was, there was a lot of struggle for us to get quality data. So in fact, this first months when we were constructing this this model, well, getting data was probably one of the hardest, one of the biggest challenges for us. Another part, we had to have at least a rough estimate of the parameters of the model. So, for instance, we wanted to know how much time a person spends in intensive care unit before death. So we had to go through lots of literature. Well, honestly, there were not lots of literature, like 3-4 papers, some of them based on experience of 8 people, let's say. So many of that data was not terribly reliable. So after we did this all, we had to calibrate the model. So here is the general approach. Again, much of this is conventional, but something is not. So let me show you what we did. So once you have the model, you apply the Bayesian approach to find the parameters. So each transition here, is a kernel. The kernel, each kernel we approximate by gamma distribution, which means it has two parameters plus the amplitude, the probability of making this transition. So you have essentially 3 parameters for each line here. And we had, for many of them, we had some prior estimates. So after that, we write this log probabilities. So since we are all physicists, we can think of this as Hamiltonian. So we have a logarithm of probability of having a particular set of parameters. So in other words, if your parameter that you choose is really far from your prior estimate, then it will be, the probability of this is low. We had a Gaussian approximation of this prior likelihood, and logarithm of Gaussian is something like quadratic function. So in other words, you have sort of a tension associated with a parameter shifted with respect to your expectation. And then there is another term which basically tells you how probable is it to observe what you see with these parameters. So for each model, you can calculate this, for each choice of parameter, you can calculate how likely the observed data are for for given parameters, and then you want to maximize this log likelihood or entropy, if you wish, or Hamiltonian, minimize Hamiltonian. So different ways of putting this, but of course the way to do it is you do it through Monte Carlo, more specifically Markov chain Monte Carlo procedure. So you have multiple runs of this model. Each time you change parameters somewhat, and then you get this, you explore this huge parameter space, and the output is you will get some curves, which I will show in a moment, and this is the slices of this parameter space. So each two-dimensional image here is a set of two parameters. So for instance, the time of staying in IC in intensive care unit, and root mean square deviation of that time, things like that. So the thing to learn from what you see here is that actually you have a very decent behaving model, because you have well-defined Bayesian of attraction. It doesn't split into different, sometimes when, well, in early days, we would see very bizarre shaped, I would say probability distribution functions for those parameters, and that was the signature that something may be wrong. So again, this is a set of parameters. We of course then look into this posterior and looked whether something made sense. So I will give you one example. So again, it's close to my heart because I spent so much time getting those priors. So at some point, that was a real gold mine. I found this report of Association of Intensive Care Units in United Kingdom. So they had this magnificent statistics of people who went through ICU units. We knew what is the probability of survival. We knew what is the probability, what is a full-time profile, how much time a person stays in intensive care units. So we took this as our prior. And then when we started to run it on data mostly from Chicago, but also from Illinois as a whole, and later in New York, we found that the average time that the model chooses is way shorter. So for instance, to give you specifics, the average time to stay in the United Kingdom in ICU was 13 days. The average time in the United States was 6 days. And then turned out once more publications started to appear, we started to see that actually that is true. That is, there was a huge difference in how, can you see me? Okay, yes. Okay, so there is a huge difference how different healthcare systems actually function. So somehow model was able to capture it. So this is basically more or less how the inputs and outputs of this model look. So one of the key things that we can do, we can plug in different data streams. So you would think it's a trivial thing, but turns out that not many models on the market actually do this. So what you see here is okay, so what you see here are four type of data, in fact, for a state of Illinois. So this topmost is number of people in hospitals. This is number of people in intensive care units. The solid vertical line shows the date at which this model was run. So it was calibrated on all these data points before that point. So this blue and gray are different type of deaths. So we had an access, eventually we had an access to data directly from hospitals and also data reported by the state. They were not the same because some people would die outside of hospital. So we use these three data streams to calibrate our model, and then let it go. So when I say let it go, you have to understand that, well, there are some things we cannot possibly predict. We cannot predict, for instance, that people will start, getting around and go to restaurants and things like that. So we could only run the model under assumption that, for instance, the level of mitigation will stay the same. Our level of mitigation will get relaxed by a certain percentage. So there is no way we can do better because it's behavioristic part of the thing. We can only say that if everything stays the same, then here is how the model will go. So as you see, these are the data until early June, which is more or less the whole period of the strong mitigation. And in general, it worked fine. In general, it worked not bad at all. So you can see the two runs of our model. One was this first run, this upper picture corresponds to the date when Nigel went to that press conference. It's April 20th. This one is a month afterwards. So as you can see with naked eye, the predictions over 1 month haven't changed drastically. So they're more or less consistent. Another cool thing that we observed is that from this model, we could extract how the effective reproduction number was changing. So originally it was roughly 2.5, but then it went down, and you see it didn't go below 1, which means that we didn't really stop the epidemics from spreading. It took some time for it to cross this 1. We will talk later why this eventually happened. Now, what you see here is that this social distancing factor, M of T, that measures how much this reproduction number is reduced, it follows remarkably close. It was very close to different measures of mobility. So this is, I believe, Google's measures of mobility at workplace and transit stations. Mind you, this particular observation that it was proportional in early days of mitigation doesn't mean that it keeps being proportional in the future. For instance, we had massive acceptance of masks, and that, of course, changed reproduction number dramatically. So you cannot say that correlation is causation here. We know for a fact that since then, mobility in many respects came back to what it was, but the mitigation factor is no longer. It didn't come back to 1. Definitely, we are not in the regime we were in back in March. Okay, so several questions at this point. So number 1, did it actually help anyone? That's very much an open question, honestly. Here is a picture of two cases that are close to our team, because, well, I'm in New York and my teammates are in Illinois. So you can very clearly see the sign of this early intervention in Illinois. Yeah, you should, of course, disregard these jumps like this. It's mostly underreported deaths which were reported later. And again, I'm using deaths as a most reliable measure. The cases were changing mostly because, well, primarily or to large extent because the testing was changing. But you see, originally there was this really fast growth, which was roughly doubling every 2 days. Then there was this very sharp change. And for a while, it was still exponential, but with very different doubling time. So this change in this curve appeared roughly in the middle or middle April. The shutdown occurred on March 20th. So there was a delay which is 25 days, which is consistent with many of the most of the parameters that we are using. So the typical onset to death is 18 days, so that's a conventional number. And then between onset and time of infection, there is another 5 days. So it's close. This kink is well describable by this early mitigation. Now, what happens after is more curious. So you can see that New York, well, in New York, you see this kink here, which probably was, well, the contributing factor was definitely the mitigation, but it was not the only contributing factor. You can see that now New York has almost essentially zero infections, or zero deaths, but also zero infections. Illinois still has something that resembles second wave. Why is it so? Well, this brings me to the territory which unfortunately is extremely politically charged now. So we are now find ourselves in the middle of so many controversies altogether. So first of all, just to put this into perspective, our team contributed to closing of Illinois in the first place. So and Nigel and Sergey were the faces of basically scientists who advise governor. By the way, of course, there were also teams of epidemiologists, so I don't want to say that we were the only ones. There were two teams of epidemiologists and one team which happened to contain only physicists. And of course, the governor was taking into consideration all those recommendations, and they needed several opinions, of course. Now, well, they normally would look at the worst case, which we never were. So we actually were very optimistic in most cases, which turned out to be close to truth. Now, the discussion that is going on in the United States these days and elsewhere in the world involves the term herd immunity, right? So just last week there was this huge discussion in Senate surrounding this. Specifically, the question is New York doing anything better than anyone else, and that's why it has zero infections? So I would argue no, that's not really the case. So there are other states who are doing just as well, who have all the same measures. So one noticeable example is actually California, but they cannot put under control epidemic fully under control to the degree that of almost extinguishing it. And the reason is, I will argue, is that we have some signs of at least partial herd immunity. I would rather call it communal immunity, by reason I will explain in a moment. So here is a qualitative observation, which is pretty much in your face. You can see 4 parts of United States. Northeast, which was very hard hit. So, yeah, Northeast includes New York, New Jersey, Massachusetts, Connecticut. So this northeast corner of United States. Then Midwest, which was medium hard hit. Well, honestly, it was still hard hit. If you compare the numbers to pretty much any country in Europe, it's comparable. It's probably comparable to most of Americas too. But in that case, we need to I have strong suspicion that in many countries, including Mexico, we have lots of unreported deaths, and we need to compare their excess deaths, excess mortality, really. Then there were these two regions in the United States which were relatively spared by the first wave. So this level of 2 to 3 deaths per million is actually not terrible, let me say. Just compare where we've been in Northeast, and New York was even worse. Now, as you can see, during the second wave, which in the United States occurred starting in July, when most of mitigation was removed in many states, there was a reversal of fate. So those who were very weakly hit, especially South and the West, actually experienced substantial second wave. And those which were slightly hit, well, strongly hit originally, well, like Northeast, didn't have anything like second wave. The Midwest had very mild one. Okay, this by itself is already very strong evidence that it's not really that some of the states are more competent than others. There is a real underlying force that does it, and the natural explanation is that, well, you just run out of susceptibles, right? And this is the problem, because by no account we should be close to herd immunity. The worst hit areas in the United States are still in New York City. In New York City, probably by different estimates, has between 20 and 30% people who have been infected. So traditional paradigm that herd immunity is achieved when number susceptible is 1 over reproduction number. So if you assume that your reproduction number is 2 to 3, you would get this value 1, well, number of remaining susceptibles should be between 30 and 40% herd immunity. Of course, if you actually do something, if you try to suppress the epidemics, and we all do, we wear masks and everything like that, so that number should be corrected. You see, the herd immunity, the term herd immunity is a relative term. It's often used in a very crude manner. People say take original reproduction number, and they say, okay, once you achieve the herd immunity that's associated with that number, then everyone is safe. Go have fun. The point is, this epidemics is complicated. So at any moment of time, we have some level of mitigation enacted. So we have, again, I mentioned masks, I mentioned social distancing, we might close schools, we might reduce the amount of people working, more people might work from home, etc. So in other words, the real story is in between. We have a little bit, well, we have substantial level of mitigation, but we also are being helped by this correction to herd immunity. Now, here comes the important observation. The herd immunity is known not to follow the classical estimate. It is known for a while. It is known for, well, it is known in physics community for at least 20 years, because people were interested in heterogeneous system, and especially on spreading of epidemics on the network. It was known in mathematical, in applied math community dealing with epidemics also for a very long time. So it is known that if you have heterogeneity in your system, it universally suppresses herd immunity. There is a very simple explanation of this. So back in the times when, in the heydays of network science in early 2000s, physicists tried to propagate the idea that one can do a smart smart immunization on a social network. If you find your hubs, you should immunize them. In this way, you can actually stop epidemics much earlier. Now, what actual epidemics does, it does that for us, because of course people who are social hubs would have high probability of getting infected and essentially developing immunity. So conceptually what happens there is that indeed you preferentially knock down people who are actually responsible for a lot of transmission. The details, the mathematical details are more delicate, so you have to consider different things. So first of all, you have to consider that susceptibility of different people may be different. Second, you should consider a case when individual reproduction number might be different. Importantly, if your reproduction number, individual reproduction number, how many people you will infect, is completely uncorrelated to your susceptibility, that will not change anything. So you can simply average your reproduction number over your whole community. Only the part that is correlated with susceptibility is important. So it turns out that I can start, for instance, with the same equation I've shown you before, assuming certain distribution of this susceptibilities alpha and certain value of reproduction number for given alpha. And then what we managed to do, we managed to rewrite this set of equations, this is set of equations parameterized by alpha, as very conventional homogeneous equations of evolution by introducing, we basically coarse-grained the problem, and we did it exactly. So we had to introduce, in order to do this, we had to introduce several parameters. First, we had to introduce the overall number of susceptible in the population. So it turns out that for any value of alpha, for any susceptibility, it will go down exponentially with this value of alpha. With certain coefficient z, you don't need to worry about what that z is. In fact, it's an integral of something here. It's called attack rate, but integral attack rate. But what is important is that the total number of susceptible and total and effective reproductive number, which are right here, they are the function of the same scalar quantity z. So in other words, they can be parameterized by each other. So to emphasize, we can rewrite the equations. I didn't write it for, just don't want to overwhelm this here with too many equations. We can rewrite the equation for evolution completely throwing out any of those indices that correspond to individual susceptibility. All you need to know is the relationship between number of susceptible people and effective reproduction number. Traditionally, in homogeneous case, this relationship is straightforward. One is just proportional to the other. If you have only 50% of susceptible left, your effective reproduction number will be reduced by a factor of 2. So in our case, however, it is not how it goes. As the size of the epidemics increases, so this S decreases, the effective reproduction number will be depressed, and it will be depressed proportionally. Originally in very early stages of epidemics, it will be proportional to the size of epidemics, and this coefficient of proportionality need not to be 1. This is an expression for it. So you can, if you know the statistics of your susceptibility, you can actually calculate this parameter lambda. This parameter lambda I will call immunity factor. I will show you why it's so important. But now let us consider a very simplified model. We will say that my susceptibility, the probability that I will get infected, depends on 2 contributions. One is social, it's how likely am I to have contact with other people. And another is biological. I might have compromised immune system and therefore more susceptible to get infected. So then if you assume that the 2 are uncorrelated, well, again, big assumption, but let us assume they're uncorrelated, then you can assign you can split your immunity factor, this lambda, into 2 factors, into biological one and social one. The social one is related to all these old network studies of, old being 20 years ago, network studies of spreading of epidemics on a graph or on a network. This biological is more trivial. It just tells you that each site have a finite probability of getting infected, which is individual. Now, since social and biological are different, so social is two-way street. If you have higher social susceptibility, you have also higher infectivity. You have, if you have more chance of meeting other person, you just are at higher risk, and you are putting others at higher risk. So as a result, interestingly, mathematically, you simply reuse the same formula you write here, and now for social, you just say that your individual reproduction number is proportional to your susceptibility. So in other words, it's your social strength or degree of yourself on the graph. So in this case, if you assume this proportionality, you will get this very interesting expression for lambda. It's third moment divided by first and second moment. Now, it turns out that we know a lot about social networks. No shit, right? So, I mean, people were studying this for 20 years. They were studying this on real people. They were, there is a lot of activity where you either follow people by using their cell phones or put radio frequency ID devices on people, and you can measure the time that people spend face to face. By looking at this data, there are lots of those, you can observe one very interesting thing. Despite the circumstances being very different, sometimes this is measured in a museum, sometimes in a scientific conference or for students on campus. What is very common is that the distribution function of the degree, or number of people you contacted with, or of the time you spent with other people, just follows exponential distribution. That's it, just exponential. For exponential distribution, this thing is very easy to calculate. It's just 3 factorial divided by 1 factorial by 2 factorial. So the answer is 3. So this number is 3. There's biological thing, it's somewhat harder to extract, but you can look at case statistics, for instance, and try to figure out how more likely or less likely you are to get infected depending on your age. Again, that is not terribly reliable. We will have better understanding of this once enough antibody data is available. But turns out that this prefactor is subdominant. So we calculated it So as I told you, this thing is 3. This thing we calculated for specific case of statistics of New York City. It was something like 1.3. Again, it's relatively small correction to this 3. So this way of estimating this parameter gives us number 4. What does it mean? So first of all, I told you this tells you how much reproduction number will be reducing in the beginning of the epidemics. So it will be reducing much faster than in homogeneous cases. In homogeneous cases, it's this number is 1. I estimated this to be 4. So that's important. In other words, early on, removing 5% of susceptible is equivalent to removing 20% of susceptible if we were talking about homogeneous model, if you compare to homogeneous model. Okay, so when you talk about heterogeneity, it is often associated with another phenomenon. This phenomenon you probably have heard by now many times. It's called superspreaders or superspreading events. It's when one person happened to infect many. So you can see here the observation that if you take well, what is the best way to show this? Well, the general observation is that, oh, look at here, that 20% of infectious case of primary cases will result in 80% of secondary cases. This is the famous paper that introduced the notion of superspreaders after SARS epidemics, and we now know for sure that it is the case for COVID as well. So COVID is very heterogeneous, heterogeneous epidemics. Very small people, a very small percentage of infected infect a lot. Now, can you use this data to predict this reduction, this renormalized herd immunity threshold? Turns out that no, and the reason is, okay, we thought it's so important that we made it into basically a title of our paper. What we care about is, for some reason, is persistent heterogeneity, not short-term overdispersion. So in other words, all these events that contribute to super spreading, they occur on a very, very short time, typically a couple of days. So all you need is just to be in very infectious state and go to a party. That is not necessarily, that doesn't mean that you are a party person. You just have been in the wrong place, wrong time. This is very different from what we call persistent heterogeneity. Persistent heterogeneity is when you, for instance, a politician or a doctor or a teacher and have to meet other people, or policemen, and have to meet the other people very often. So you are under higher risk to be infected. So that's why you cannot use the statistics of super spreading to calculate this parameter lambda that I mentioned. So here is the prediction that we get. This banana-shaped curve simply corresponds to different values of lambda. I mentioned that our estimate is lambda equals 4, but let's see what happens if it's between 3 and 5. So according to our estimates, places like New York City would be close or even below this herd immunity, well, buff rather, this herd immunity range for COVID-19. So that would explain to some degree why New York is showing so little infection these days, whereas Chicago is not. So there you of course also reduce your effective reproduction number considerably compared to classical result. Classical result is this dashed line, right? So this dashed line is just proportionality. So in fact, you go much steeper, but still not enough to get herd immunity. Now, what is often forgotten when people talk about herd immunity is that you don't stop once you reach herd immunity. If epidemics is ongoing, there is a so-called overshoot. So you go to another value, which is known as final size of epidemics, which can be way, way, way farther from herd immunity. In fact, in classical case, when they say that herd immunity corresponds to 60% of people ever infected, the final size of epidemic that corresponds to that value is something like 90%. So this is exactly the reason why it is unlikely that this classical picture is really valid. We don't know much of the epidemics that go that far. Something else stops epidemics. The heterogeneity is one of the possibilities. The mitigation, the fact that people get scared and stop seeing each other, in other things. So this psychological response and of course government response, all of this probably contribute. Now, here is the comparison to actual data. So of course, this is not a direct data. We took our model, the model that I've shown you originally, we extracted the value of effective reproduction number as a function of time, and then plotted it against their estimate or calculated susceptible population fraction. So blue here, blue data points here correspond to New York City, and red correspond to Chicago. This other set is the same thing, but we corrected for the reduction of mobility. Remember, we saw that mobility actually changes the reproduction number. So we just corrected for it, and it didn't change much of this slope. This slope is the thing that matters for me, because this is my this is a direct observation, if you wish, of this immunity factor. And you see the best fit is somewhere between 4.5 and 4.1. So it's actually remarkably close to the estimate that I gave you. So if this is the case, then what would one expect for the second wave? Okay, so this is, by the way, our phase diagram. So remember, I mentioned that the herd immunity, the classical herd immunity for, let's say, for reproduction number 3 would require at least 60% to be in people of being infected, but the final size of epidemics is 90 plus. So it is huge, it is humongous. On the other hand, if you include this heterogeneity and say that it's somewhere between 3 and 5, this lambda is between 3 and 5, what we estimated, this reduces the herd immunity threshold. Depending on your R0, it can be anywhere from 20 to 30%. And the final size of epidemics can be, well, anywhere in this range. So it can be as high as 50 plus, or it can be as low as 25. Depends again on your parameters. So you have to appreciate the complexity of the problem, because in addition, you don't, this number here, of course, is not constant. You mitigate it. You try to reduce it. So as a result, your overall behavior is much more complicated. The behavior of the system is much more complicated than just this simple phase diagram. Now, this is a demonstration of scenarios that you expect based on this corrected theory. So for our case of lambda equals 4, you should follow the green line, which you almost don't see here. So for New York City, you don't expect any the second wave if you completely remove the mitigation. But there are warnings there. I will tell in a moment. In the case of Chicago, again, these predictions were made in mid-July, and it more or less follows this green curve actually since then. So you expect really, actually probably even less than that. So you expect the second wave to be actually smaller than the first one. Now, the warning, the very important warning. So I mentioned that everything works only as long as this heterogeneity is persistent, but it is not, right? If you have particular friends today, it doesn't mean that you will have the same friends a month from now, or the same people you will be talking to actively interacting with a month from now. So there may be a relaxation in the rewiring, we call it, on the network. So if there is a characteristic time over which this rewiring occurring, then all claims are off. So this herd immunity, that's why I don't like the term herd immunity, it has a strong social component. It depends on you preserving the same pattern of interaction during the whole time of epidemics. If you change it, very simple example, people go, it's 1st of September, people go from their native town to campus. Their social network rewires immediately. People go to, kids go to school, their social interaction pattern changes dramatically. That's why this so-called herd immunity is very, very fragile, exactly because you can have this rewiring of the network. So we included in our model now this factor that deals with this rewiring, and look what happens. So this is in the Gedanken experiment. You achieve what seems to be a herd immunity. You don't see any second wave. The mitigation is completely removed at this time, but underneath, under the hood, something is changing. The people change their context. They don't change average exposure. They don't change even the distribution function of susceptibility, the distribution function of their social connection, but they change individual with whom they interact. And then, whoops, after some time, well, in our case, rewiring time is 100 days. So at some times, whoops, we see the second peak appearing, then the third, etc. So you can see how eventually on this plot that in this diagram that I keep showing you, you actually will approach the actual classical herd immunity, because you will completely forget all social structure that you had initially. Okay, so I'm almost at the end. I will only mention that now we are in the middle of episode 3, trying to control an epidemics on micro scale, and scales of the University of Illinois campus. You can see the statistics of the way how we control it is by massive testing. So folks in University of Illinois developed this saliva test. They can administer at least 2 times per week to students, and the results are available within hours. So this way, that's how we basically try to control it. It's not trivial. So for instance, we had this early spike. So this initial behavior here is this. This plateau is just people coming to campus. So this is how many cases we had, because people arrived already infected. This occurred in early days of the year. Well, in middle of September. Well, anecdotally, because of fighting, but not really. I mean, it's more complicated than that. But of course, well, after that, there was a local lockdown. So the university just said, okay, no fighting, essentially. So there was imposed lockdown. It helped to mitigate that thing, but now we still see some creeping up. So we still actively trying to control it by inventing new ways of having this feedback loop. But our biggest achievement, of course, is getting to this comic strip here. So it was, I don't know if it's a good or bad publicity, but at least now everyone knows about our exercise on campus. So thank you for your attention.
Thank you very much, Alexei. Sorry, I was laughing at the
Yeah. Okay, it's intended to be.
One thing that it could be achieved is like physicists would be invited to more and more parties, right?
Yeah. I hope so. I mean, yeah.
Okay, thank you very much for this excellent talk. Actually, I think I enjoyed it a lot personally. Now we have time for questions, please, and remember what is the way to do questions. Maybe either you can write it on the chat and I will read them, or just simply unmute your microphone and ask directly to Alexei.
Yep.
Please go ahead. Questions?
Hi.
Hi.
May I ask a question?
Yes.
Go ahead.
Okay. Well, thanks for the presentation. I think I missed the part when you mentioned the herd immunity or the immunity status of the population. How
Yes.
do you measure or track that information? Or
It's very hard. Yes, it's very hard. So our best way so far is, let me go up, is this plot. So what we observe here is, since we have this epidemiological model that is calibrated by the known number of deaths, hospitalization, and ICU usage, we can extract the current value of effective reproduction number. So it's what is written here, RE. Oops, RE here.
Okay. So do you use the effective reproduction number to like infer what would be the immunity?
Yeah, we basically see how effective reproduction number changes as susceptible population decreases. And by looking at the slope, we deduct that it doesn't follow the classical line. The classical line would have a slope 1, so it would be much shallower. So from what we observe, so in terms of actual dynamics, you can look at this orange curve here. So this is Illinois. So I mentioned that what happened is, due to original mitigation, we had this first cusp, right? So we know for a fact that after this, nothing was, the regime never changed to anything more restrictive, because it was the other way around. People actually were very serious about quarantine initially, but then it relaxed. However, you can see that the orange line keeps going down. So this curve with which it goes, it actually contains information about how it becomes slower as susceptible population is depleting. And if you just take standard model where one is proportional to the other, the effect would not be strong enough to account for that. So basically that's what we are doing. So we are saying the effect is stronger than that. But again, the real problem, so why I really resist calling this, I don't like the term herd immunity by many reasons, but one of them is the following. Yes, during this time, we claim that this parameter lambda that we say is close to 4, but it doesn't tell much, or it's really stretch of imagination claiming that it is still 4 here, because it's new world after this. On July 4th, you relax quite a bit of rules. People changed their social patterns. They went partying. It's not basically the social network had rewired. So yet again, you can sort of convince yourself that we are repeating the same story now, because you still see some sort of growth that will eventually, of course, saturate and start going down. So we might repeat the same thing again. So if I go back to my plot here, right, in this model, this would correspond to my original behavior during the mitigation. I go down, my effective reproduction number goes down as susceptible population drops. Then not much is happening. You have the second wave, and then during the second wave, you again are supposed to follow the same slope. So we are hoping that eventually we'll have enough data to check this. Maybe during the second wave we will again have this slope. That would be a smoking gun for our theory. If we had the same slope during the several repeating waves.
Oh, okay. Well, thank you. Thank you, Alexei.
Thank you, Nancy, for the question. More questions, colleagues? Just unmute your microphone or write it on the chat so I can read it. Well, in the meanwhile, I would like to ask one question, Alexei, which is so now that you have actually I love your work very much, and actually I really enjoyed it a lot, and I think it's very for me it's becoming very seminal. I love the part of heterogeneity and how it impacts what you call herd immunity, which is fragile. I completely agree with you on this. So now that we understand that, and if you were to design mitigation strategies, either pharmaceutical ones,
yes,
and also combined with vaccines that will happen anytime soon,
yes.
Can you derive an optimal strategy?
Yes, I think I can. So I'm
actually
still.
Alexei, let me add one thing.
Yes.
There's always an optimal strategy that maybe everybody stays home, and that's not the must be an optimal strategy that
I understand.
impacts the economy as
of course. Yes. So yes, I think this question is more relevant again for the future epidemics, simply because one way or another, I believe we will go through it. We don't have anything or any indication that we have the growth rates comparable to what we had in the beginning. So, but in general, here is the thing. So there is a school of thought that you should not do anything and go for herd immunity. So there is this school of thought which somewhat awkwardly is considered to be a Swedish approach, but it's not, right? Because Sweden actually put quite a bit of mitigation. It just was not the type of mitigation that would work in other countries. So their government politely ask their citizens to execute social distancing, which of course in your country and this country would not work, right? So I mean, anyway, there is this naive idea that if you don't do anything and herd immunity is not particularly far, well, not terribly far, you will get there and that's the end of the story. The problem is that where you will end up is this final size of epidemics, not in herd immunity. Second, again, as I told you, herd immunity is a fluid concept. So it's not, if the herd immunity is 20%, okay, maybe. If that herd immunity is 60% eventually, then at what cost, right? So what I think is right, is absolutely right, is once you definitely have the strong epidemics with very high growth rate. Well, first of all, I mean, that comes without saying that your first strategy should be containment. So we know that there are countries like, there is a country like Vietnam who managed to completely contain epidemic and never having any serious serious incidents there. There are countries like South Korea who had a really powerful outbreak, which they managed to get under control, right? So again, it's believed that it was mostly contact tracing, but I, at the moment, don't believe that was the case. We modeled a lot. We tried to understand how contact tracing works, and I can tell you, it was not contact tracing by itself. Contact tracing helped to clear the specific cluster they had to deal with. So partially because their outbreak was so focused on one particular community, they could run behind them. But on top of this contact tracing, I believe everything they implemented, of course, they had masks to start with, right? So the actual spreading was probably such that that contact tracing would work. So my point is that if we did contact tracing in early days in New York, we would fail. Even if we had institutional capacity of South Korea at the conditions of the epidemic it wouldn't work. So there is a reason why you should go to lockdown, and very strong lockdown very early. The main reason is not so much to prevent the overshoot, that's also true, but primarily to buy yourself time. So what changed over this time that we went on lockdown, we built at least partial infrastructure of testing. We learned more. So it's just, it's very common sense thing. You're just, in most cases, not prepared for epidemics. It was shame that, we had time. We had time to prepare. We knew about epidemics since December, and that when it arrived, you've probably seen the same in your country. So no one was prepared. So there is an advantage of going to this deep lockdown, but not long, because again, from point of view of sustainable model, it's pointless, right? You just stop it and then you release it. It goes exactly where it was, right? So this time should be spent on mounting this capacity. Once you have this capacity, you can gradually go back. It's important to go gradually, exactly because you don't want to get to overshoot. So eventually you have some level of sustainable mitigation. So you know that, some people might not like masks, but it's not the end of the economy if everyone is in masks. Okay, so that's not a painful thing. Even requiring, let's say, only outside eating is also not terribly damaging to the economy. So there are different levels of mitigation that you can afford without crushing everything. So at that level of mitigation, you have particular value of the reproduction number. If that value is not below 1, well, you don't have choice. You will have to get to herd immunity that is associated with that number. Let's say you're at 1.2. Okay, at 1.2, traditionally you would say that you need to, roughly 20% people should be infected. What we say, this is an overestimate by factor of 4. So basically, you need this 5% of people removed, and then it will be manageable. It will go to manageable state. But you don't need to go through overshoot, and that's why you need to release it slowly. This way, you will drive yourself naturally to this to this value of R0 = 1 or RE = 1. Actually, many countries probably intuitively do exactly that, because each time, and there is, we have in our group, we have this term for it. The term is self-disorganized criticality. So we had multiple questions. So back in the days, I've shown you Chicago, Illinois. So we had this, what seemed like a very, very long plateau. And now, of course, I can take Mexico and Brazil, and you will also see this very, very long plateaus. This also qualifies as a very long plateaus. So we see multiple cases. In fact, if you take global number of deaths from COVID-19, it follows a plateau. It's almost steady. So what is the origin of this, we thought? And the most natural is that you have this social feedback, right? So if things go really bad, people are scared, they actually, they reduce the reproduction number. Once it goes down, then everyone is relaxed and goes up. So as a result, this is sort of an attractive point to which the population naturally goes. So it actually is locked to this R0 equals RE equals 1. And of course, the more as the number of susceptible reduces, this attractor corresponds to less and less mitigations. And this way, it's actually a self-organized, we call it self-disorganized dynamics. That's why, partially because of this and because of all this insight we get from running these simulations with heterogeneous, I'm actually cautiously optimistic about where we are going. Again, depends who are we, right? Because, okay, I'm in New York City, I'm in New York, and we are so hard hit that it's probably a safe claim that we'll never see anything that was here in the March. From what I see in let's say Mexico City data, in a sense, it's very similar situation. It was spread over time, but the final hit was probably comparable to New York, so it's fairly hard hit. So it is unlikely those hard hit area will refire unless we seriously misunderstand how long-term the immunity is. So we know that the immunity wanes, we know that there are reinfections. So at the moment, there is a feeling that this reinfection is just, well, it's probabilistic. So some people get lose their immunity and get reinfected, but it's not something that can truly reignite full-scale epidemics. So in that sense, I believe that the countries that were already hard hit probably will not have big problems. Countries who actually managed to mitigate the first wave very well, they're now finding themselves in somewhat harder situation, because you cannot convince the population to sacrifice anymore, and they didn't reach any level of herd immunity, so they have to find this balance somewhere. But if you look globally, I mean, it's never anything at this stage. Like if you look at the second, third wave, it's never anything terribly dramatic. I mean, compared to the first wave, it's always sort of weaker. The strongest now is probably somewhere in Israel. So Israel has a third wave now. They to the degree that they had to go to lockdown. Even there, if you look at the measures like deaths per capita, then of course it's nothing compared to what Lombardy or New York had in the early days. So yeah. So in other words, I mean, somewhat intuitively, many countries who got the epidemics eventually probably worked reasonably close to optimal. The hardest thing, I mean, the biggest mistake that was made by many countries is didn't shield all the population. So I mean that was a tragedy here in New York. I know that. I mean, if you now look at data, for instance, and compare New York to London, the most striking difference is really the attack rate among all the population. So New York, unfortunately, completely screwed up, and London managed to at least suppress somewhat this thing. We know that Sweden, for example, also had this issue. I mean, they didn't, despite their best attempts, they didn't contain it, and they had lots of people in nursing homes died. So yeah.
Okay, so thank you very much.
Sorry for so many words. So yeah.
Thank you very much. More questions, colleagues? If you have questions, just unmute the microphone and ask. And if not, shall we thank Alexei in the old-fashioned way? Shall we unmute the microphones and applaud Alexei for this magnificent talk? So thank you very much, Alexei.
Thank you, guys. Thank you. I hope to see you one day in actual Mexico City.
Yeah, of course. You were invited this time virtually to Mexico City, and when everything, all this mess passes, of course, you are more. Yeah, thank you very much, Alexei.
Yeah. Okay. Bye, guys.
Everybody. Bye, bye.